Hi everyone! Thank you for waking up just for me. I am honored and I'm super excited because it's my first time here talking and versing, so I'm excited. Let's start. So my name is Mey. I am a Node.js developer. I'm a software engineering graduate and I'm a huge Star Wars fan. Yes, these are R2-D2's heels. So I have to tell you about my last semester in college. So during the last semester of college, I had 10 courses left to take. 10. And oh yeah, I had to work 3 times a week. And having to balance between work and college, I had to have the best timetable. So let me show you how I assembled this timetable. So when I had to start to assemble my timetable, this is what I had to do. I have the list of courses, and lectures are mandatory, and tutorials you can choose from this list. So let's say we want to choose the calculus course, because that's what I want to do. So I choose the mandatory lecture on Sunday, and also the tutorial at 9 a.m. in the morning, because that's my favorite hour. So we chose these courses, but when I choose a class, I want to consider my own constraints. So the first constraint I had to consider was the minimum school days. I don't want to be there if I don't have to. And I didn't want to have too many clashes between classes. Well, I can't be in 2 different places at the same time. And also I wanted to have minimum gap between classes because I didn't want to wait for a class for more than 1 hour. So let's go back to the list of courses and see if what I chose was good. Okay, so I chose the lecture of assembly. It's 9 a.m. in the morning on Sunday, and also the tutorial, and it's at the same day, at the same hour. That's it. I violated the clashes constraint. And sometimes it might be okay to violate this constraint. Maybe I don't have to be at the entire lecture, but I want to try to avoid doing that. So let's try to re-choose this class. So now I went for the Wednesday tutorial of calculus. Let's see how this timetable looks. And okay, that looks good because I don't have any clashes, I don't have any gaps, but I have to go 3 times a week. And I might want to try to re-choose again. Maybe I can do it a little better. Okay. So because we violated the minimum school days constraint, let's try to re-choose again. And okay, so now I re-chose the assembly tutorial. I moved it to Wednesday. Oh my God, that's a perfect timetable because now I only have to go 2 times to college. There's only 1 hour gap between classes and there are no clashes at all. So notice how it took us about 3 to 4 minutes to assemble this timetable. It was only 2 courses, and well, I prepared this example. I knew what to expect, so it was easy. But try to imagine if you had to do that with 10 courses. That's a lot. So I had a problem, but not really. I'm a programmer. I can program my own timetable generator. Yes. Okay, so I had to define my problem. My problem is a constraint satisfaction problem. What does it mean? It means that I have constraints, and a solution is a timetable. And a timetable that answers all of the constraints is the very best solution. So, just like a good student, what I did was I turned to recursion, because that's what you know when you're in college. I tried to solve this problem with one of the most famous constraint satisfaction algorithm. It's called backtracking. So backtracking, what it does is it goes through every possible solution and it searches for the very best solution. And if it exists, that's what will be returned out of the backtracking. So when I inserted 2 or 3 courses, it worked great. But then I inserted 7 courses and 8. And I waited and waited and waited, and the answer from the recursion never returned. A quick calculation suggested that I might even wait 2.5 million years for that solution. So I didn't have that time. The semester was about to begin. I had to revise my strategy. Maybe I don't need the very best solution. Maybe a good enough solution is also good enough for me. So, everyone, we're going to talk about today the genetic algorithm. Okay, but before we begin, let's take a look at a quick background. Okay, flowers. Let's say that the red color is the strongest color, just because that's my favorite color. So, if we have the initial population and we combine them together, the best qualities will move forward to the next generation. And then this generation creates another generation, and the best qualities, the fittest qualities, will stay on forward to the next and next and next generation. And we are a very good generation ourselves, and I think nature did a pretty good job, so why not use that to solve my problem? So genetic algorithm, let's see how we use that in our problem of the timetable world. Okay, we start with generating an initial population. Then we move forward to the fitness step. This is where we grade each solution, meaning that we determine how good a solution is. Afterwards, we have these three steps, the selection, the crossover, and the mutation. All of them together are called the reproduction part. And this is where we create new solutions out of the existing ones. And how do we stop the algorithm? Well, there are two ways. Either we can stop after a number of generations, or we can stop after an amount of time. And it's important for me to say this. Just because you let the algorithm run for a longer time, it doesn't mean you'll get better results. It's not necessarily. So it's all about exercising trial and error. Okay, let's dig deeper into this algorithm and see how it goes. All right, the first step, generating an initial population. So we had the timetable problem. Just please notice that over here, it's number instead of names, because I thought it will be easier for you to see. Just assume that these are classes. Okay, so a solution is a timetable. Many solutions, they construct a population. And many population is all of these populations together, they are many generations. Okay, how did I construct a solution or the initial solution? What I did was I randomly chose courses out of the courses list, and I inserted them into a timetable. So even if I got not so good timetable, let's say I had too many clashes, all of the courses, I had to be at all the different places at the same time. It doesn't matter. I'm going to deal with the invalid solutions later on in the fitness step. So right now what we're doing in the first step is just generating random solutions, even if they're invalid solutions. Okay, the size of the population. So what worked for me was 100 solutions. 100 solutions per generation. And how did I find that out? Again, it was all about exercising trial and error. So if you have a wide range of solutions for your problem, I suggest that you'll have a wider range of population, because then you can cover a wider range of solutions per iteration. But don't have a too big of population, because then it will influence the performance of your algorithm. So again, exercising trial and error is what works here. Okay, now that we have a population, each of the solutions is randomized. So what I want to do now is grade each solution. I want to determine if a solution is good enough or not, or how good a solution is. How do I do that? So the grade for each timetable is constructed out of the three constraints that I mentioned earlier. And I worked with lower is better because I wanted to avoid negative grades. And let's take a look at how I did that. Okay, I'm going to start with the simplest constraint, and it's just the number of days that I have to be in college. So each time there is a day, it gets a penalty. Let's take a look at an example. It's the simplest way to explain. So a penalty per day is 10 points. And here we have 2 days. It means that the grade for this timetable, for this constraint, is 20. But it's only this constraint. The amount of days per timetable got the grade 20. So now let's move forward to the next constraint. The gaps. So a gap got 10 points penalty per hour. So over here, there are 5 hours gaps. Over there in Sunday, there are 3 hours, and then 2 more hours on Wednesday. So all in all, that's 50. The grade for this timetable, for this constraint, is 50. So the entire grade for this timetable that is constructed out of all of the constraints will be 70, because we had 50 for the gaps, and then there are no clashes at all, so it's a 0 right there, and 20 for a number of school days. So remember, lower is better. Let's take a look at another example. I think it will help you to understand better. Okay. I want to talk about the clashes constraint because this is a problematic one. So if I have too many clashes, then it's an invalid solution because I really can't be in so many places at the same time. But sometimes if I have to miss just the first half of a class or the first half of a lecture, that's okay for me. That's a valid solution. So this is why I wanted the clashes to have a higher penalty than the other constraints, but still, every solution that is generated is actually valid solution. I just wanted it to have a higher grade, so it will express that this is not a good solution, not like the other ones. So over here, you can see we're already at 100, and it's just for this constraint. So that's pretty high, because what happens here? Too many clashes. Okay, so the overall grade for this timetable is 120. So it's not such a good grade, but I still want to have this timetable as an option in the entire generation. Okay, this is the entire fitness function. I would like to advise you again to exercise trial and error. This is what helped me determine the size of the penalties. How big? Do I want to have one penalty higher than the other one? So that's what helped me. Again, trial and error. Okay, now the next steps are the reproduction. What we have is a generation. Each solution is graded. Now what I would like to do is to generate new solutions out of the existing ones. How do I do that? We start with the selection step. So the selection steps talk about choosing the parents. And those parents will generate children. Or not children, just solutions. Okay, what did I do? I chose to work with the roulette wheel selection. Why? Because this selection helps me to have better solutions, to have better chance of being chosen as parents. How did I do that? Oh, it's really important for me to say that there are many ways to do the selection part, but this one worked great for my project. So again, what did we say? Yes, trial and error. Okay, let's take a look at a quick example. Let's say that we have only 4 timetables as our generation. Each timetable is now graded. Over here, you can see the fitness grade. Okay, so now I wanted the grade to express the chance of being chosen, not the fitness. So if green is the best timetable, I wanted this timetable to have the best chance of being chosen as a parent. So now it got the highest grade. I summed all these grades up because I wanted to normalize the results. And now what you see over here, these are percentage. Percentage of what? Of the chance to be chosen as a parent. All we have left to do, generate a random number between 0 and 100, and that's the parent you're going to choose. Whether it's this one or the other one, but they all have the chance of being chosen. Okay, we chose the parents. Now what do we want to do? Children. Okay, let's move forward. So I chose the 1-point crossover. The crossover is the step where you generate new solutions out of the existing ones. How do I do that? You select a single point to cross the solutions, and then you construct a new solution from the 2 old solutions. And I chose this crossover because it kept the order of my solution. It didn't mess around all the courses. And this is how I generated a new solution. Again, there are many ways to do the crossover. It depends on the way your solutions are built. It depends on your project. And again, what did we say? Exercise, trial, and error. Okay, this is my favorite part of the algorithm. And before we move on into talking about mutation, I would like you all to stop, zoom out of the timetable world, and come with me and take a look at a genetic algorithm game. Yes, there is a game of genetic algorithm. It's out there, online. And this is a frog. Yep, you're looking at a frog right now. What does this game is doing? Okay, let me see. So this frog is a solution. The frog, what it wants to do is to jump as further as possible. Many solutions, they are a generation. All of them together try to jump and jump as better as possible. So now over here we can see each solution trying to make its way all the way. And for those of you in the back who can't see, this is generation number 12 and the fitness is 14%. And now if we move forward to more generations, what we will be able to see is that all of these solutions, they jump together. It's almost like one solution. They're kind of the same. I mean, where is the evolution part? What is going on here? Why is it all going to a local maximum? The fitness is still 14%. We reached a local maximum because we couldn't get a higher result. So what we do, we take a look at this game once again, but now I inserted mutation to some of the population. What does it mean? It means that I might throw in an extra leg, maybe I'll throw in an extra muscle, but now what happens is that I managed to generate a bigger range of solutions that I didn't have before. I couldn't get these solutions only by getting 2 solutions together. So mutation helped me avoid the local maximum. Come back with me to the timetable world. How do we mutate a solution of a timetable? So we have this timetable and I wanted to mutate it. So what I do, I go back to the list of courses, I randomly choose a different class, and I insert it to the same timetable. What happened here? I got a worse solution because now there is a clash, but it doesn't matter. I want to keep those invalid solutions. I want to have them because this is what creates the bigger range of solutions. Okay, that was the reproduction part. Yay. And that's the entire algorithm. I know, you all have so many questions. Mey, what happened in that semester? Did you have the best timetable? Yes, I did. I had the best timetable, but I did not go to any class because, well, it was better just to study on my own. It was much faster, and then that's it. So, I know what you want. You want some code. Let's take a look at some code. But before we do take a look at some code, I would like to say that this project is out there on GitHub. I did that with another good friend of mine, and we used a wonderful API. It's all written in C#, and I advise you to go take a look. Okay, so I don't know if you can see it very well, but I'll just read it to you. So what happens here, it's the code for executing the entire algorithm. So the input will be the list of courses and the list of constraints. And then the output will be the last generation. So when I return the last generation, it means that it's the best generation so far. What I did is before I returned it to the user, I sorted all of the results that I had, and this way the user could look at the best result first. So we start with generating the initial population by sending it the courses list. Then we activate the fitness function once before the loop. And now we have the loop over here. I chose to have 20 generations, and this is the algorithm loop. So what happens in that loop is that we go in, we have the reproduction part, and this is where we produce new solutions out of the existing ones. And then we activate the fitness function, which is the one that grades each solution again and again and again until we have the last generation. Okay, now we can talk about trial and error. I don't know if I mentioned it before, but if I didn't, I'm going to do that again. Trial and error, everybody. Okay, so I have a little story to tell you. One day I came to my friend and I asked her, Liron, she's sitting right here, Liron, am I fat? And she said, well, you're not fat, but you just have to maybe eat better, maybe plan your diet a little bit better. And I said, well, you know what? I don't know how to plan my diet, but what I do know is how to write code. So I told her, listen, Liron, you're going to help me out on this one, and we're going to create together a diet planner, or in its nicer name, the nutritionist. And that's what we did. We worked together and we developed the entire genetic algorithm from scratch for this project. What does it do? So it gets a list of products that you have in your fridge and also a list of constraints. The amount of calories you want to eat per day, the amount of fat you want to eat per day, carbs, just whatever you want to insert right there as a constraint. And then what it returns is a list of products that you have to eat per day if you want to maintain your diet. And so we started to work on the algorithm. It went wonderfully. We had a great time, but then it was super slow because our range of solutions was just huge. So what we did, we started to investigate each part of the algorithm, and we found out that our selection part, we used the roulette wheel selection, and if you remember, it goes through every solution and it normalizes the solutions. So this is what influenced the performance of the project. So we had to exercise trial and error. We searched for a different selection. And we found out that tournament selection has a better performance. So how does it work, the tournament selection? It goes like this. You have the entire population. Out of this population, you randomly choose the tournament pool, which is this array. Our pool was just 4. So we randomly choose 4 solutions. And out of these 4 solutions, we returned the fittest one. So this is the tournament selection, and it's way better because we did not have to go through all of the solutions, and this is how we had a better performance because, well, it just worked much, much better. Okay, code. How does it go? So we get the entire population as an input, and then we want to construct the tournament array. We are going to do that inside this loop. Like I said, our tournament array was the size of 4. So getting randomized solutions and inserting it into the tournament pool, and then returning the fittest solution. And this solution will be the parent of the next generation. Okay? I will activate this function twice. One for the first parent, and then again for the second parent. And then I can combine these 2 solutions in the crossover step and create a new solution. Many new solutions, we have the new generation. That's it. Oh my God. So let's summarize things up. We started with talking about the problem that I had. We talked about the timetable problem. I didn't want to work on trying again and again to generate my own timetable with pen and pencil. So I turned to backtracking, which is a great solution if you want the very best solution, because it goes through every possible solution. And if there is the very best solution, it will return it to you. But it might take some time. So this is why I turned to genetic algorithm. Then we talked about the entire flow of the algorithm. We start with having the initial population, and there I said that my population was generated randomly, and even if I had invalid solutions, I kept them, which is okay, because I handled those invalid solutions in the fitness step. Remember, the fitness step is all about grading your solutions. Remember right there that you want to have a function that will generate a range of solutions, a range of grades, not solutions, you already have them. But you want to have a function that will generate a range of grades. After you graded each solution, there is the reproduction part, where we generate new solutions out of the existing ones. And don't forget about my favorite part, the mutation part. Over there, don't go wildcard. Try again and again until you see that the mutation is not too high but not too low, that it has its part, that it helps you to generate new solutions that you didn't have before. And I highly advise you to go to the GitHub, take a look at the code that Liron and I wrote, or any other place, really. I love this algorithm. It's very, very simple. And if you try to do a project like this yourself, tell me about it. I'd love to hear. Questions? Somebody, please. Yeah. Yeah, so it's a great question. I'm going to repeat it. So at the mutation part, the question was, if I get a solution that I already have in the generation, yeah, so the question was, do I check if I already have this solution in the generation? Or, okay, so previous generations, I didn't check. In the timetable project, I didn't check at all. I didn't care because I had a wider range of solutions. So the population size was 100. So, but for the nutritionist, I checked because I had smaller, and it was more important for me to be as efficient as possible. So it depends on that. Yeah. I'm going to answer in English, and I'm going to repeat the question because it's important for the video. Okay, so the question was, did I go to any genetic algorithm course, or did I learn that somewhere? No, YouTube, internet, what? Yeah?
How you discover this thing?
Oh, so what happened was I really tried to work with backtracking. I had one day to finish the project. It was the final project of the semester. And I had to search for something better because I literally didn't get an answer. And this is when I found out the genetic algorithm is good for constraint satisfaction problems. Just like this. Internet helped me. That's it. I had no choice. I needed an answer, like really quick. Anything else? No? It was all just understandable? How often? Yeah, so what you do is, I chose to do 30% of the population. So if I have 10 solutions, I mutated 3 out of these solutions. And for the nutritionist project, I actually did an extra step. I took out the very best solution each time. And because this way I kept that the best solution won't be mutated, and I just did the mutation on the entire rest of the generation. Yeah. So the rate is about how many solutions you want to do the mutation on. Anything else? No? Yeah. Okay, I'll repeat the question, yes. So what I was asked is, if I have any statistics regarding whether the last or the best solution was generated by any specific step, like was it by the mutation, or was it randomized, or was it just by the crossover? So I don't think that it's possible, but that's just my opinion. I don't think it's possible that it will only be generated by one step, because each time that I start with the initial population, I insert them, I'm making a huge mess out of those solutions because it goes through every step before I even get to the chance of checking the fitness of these solutions. So I don't even have a way to check. Maybe I can insert a check before the fitness function and also just after the initial population. That's a good question. I can check that. Okay, the question was, how did I know what to change each time? Because there are many parts of this algorithm, right? That's the question? Okay, how do I know if I got stuck on a local maxima? Okay, so I'll start with this one. How do I know if I got stuck in a local maxima? And then I'll go to how do I know which part I want to change? So local maxima. What happens is when you start the algorithm, and I just printed out all of the generations. So I saw the fitness of each solution in each generation. And if I see that the fitness doesn't change, just like we saw in the game, it stayed on the same fitness level again and again. It was always in the range, like a very small range. Like it was always stuck on like a 14%, or it was always stuck on the 30. It doesn't matter if it's a 30 is a high. I still want to see a range of solutions, of grades. I don't want to see only one grade over there. Even if it's like 30, 31, I want more than that. So this is where I knew I reached a local maxima. So usually it means that I want to change the mutation rate. This is what I saw, okay? It might change in different projects, but for me, when I changed the amount of mutation that I did, the amount of solutions that were mutated, then I saw that I solved the local maximum problem. And okay, so the other question was, how do I know which part to change? So what I did is that I just started by writing the entire algorithm, and then I changed every time only one part. And I saw if I got better fitness range, if I got better fitness results, if I got higher results. Sometimes I changed something and I got lower results. So I knew I had to go back to the previous structure that I had before this change. So every time I changed only one part of the algorithm and moved forward by the results that I got. Okay, we're done? Thank you, guys.